Hey, what's up, guys? So previously, I think we discussed some basic idea of the multiplicative function, and so today I want to quickly introduce some famous one and talk about some basic properties. And in the future, we will using a data of the power trick to give the estimate of all these functions. Okay, hope you guys subscribe to my channel. So first one I want to introduce is this Mobius function that I already previously introduced, but I want to discuss it more. Okay. So this mu of n already remember that if n is not square free, then it's 0, and if 1 is minus 1 if even distinct prime factor, and the other distinct prime vector. Okay, so theorem, this one is a famous one. If you calculate mu of d, where d is a factor of n, which is e of n. Okay, so e of n is defined to be if n is 1, else is 0. Okay, so this may be hard to see, but for example, let's consider maybe, let's say n is let's say 12. Right, so you get your factor is 1, 2, 3, 4, 6, 12. Now you can calculate mu of n. So it's 1, minus 1, minus 1, 0, 1, right? And then this is minus 1, right? So you can see the, let's see. What's this 12, right? So 12 is 2 squared, 12, 0. Okay, so total is 0, right? So total sum is 0. This is really amazing thing. Okay, so it looks a little bit non-trivial. Okay, so proof. Okay, so idea is that let's write n equals to p1, k1, p2, k2, up to let's say pn, kn. Okay, and I know that the only the distinct of them, right? So only p1, p2, pn matters. Okay, so I only need to choose. So let's say I set I is a subset of, let's say, p1, p2, pn, right? And I can choose k of them. Okay, so I need to choose distinct k of them. Okay, so this dn mu of d is basically the I, which is I choose k of them, right? So I can choose, let's say I is k, right? So I can just choose k, right? And for each k, I get minus 1 to the k, right? I just compute this, right? So it's basically k from 0 to n, minus 1 to the k, n to the k. So this is just binomial coefficient, right? So 1 minus 1 to the n, which is 0. Okay, except for n equals to 1, okay? Because for n equals to 1, you only get 1 terms. Okay, so it's 1. Ooh. Okay, so this equation, this summation of mu of d belongs to n is e of n. This equation can be used to do so-called Mobius transformation on the number 0. Okay, so let's do this this theory. Okay, so suppose somebody give you an n and d which is fixed. So this n and k which is fixed, and what you are going to compute is this d, which is let's see. Okay, so let's do this. So let's say this nk is 1, and then you need to compute some function f of n, which is defined to be which is you need to sum over n, and let's say nk equals to 1. Let me see, how should I say this? How should I say this? Okay, so I should say that, okay, so somebody give you k, and suppose you want to compute something which has some upper bound, but which is you need to sum nk and equals to, so every GCD, every guy which is comprised of k, and you sum of them, and there is a lower bound, upper bound, but I didn't write. So this guy, can be written as, let's say, f of n and e and k. Okay, so basically it's GC e and k. Right, this is trivial, right? Because if nk is 1, you get 1, right? And this guy can be written as a Mobius, right? So this is the trick that you can do this. Okay, and the D belongs to GCD with n and k. So D belongs to n and k means that the D belongs to this factor of n and factor of k, right? So this equation can be written as a summation dk mu of d n f of n, and d belongs to n. Okay, so this guy is a summation dk mu of d times, let's say, summation m f of dm. Okay, so just change things. Okay, so this guy, these two equations are important. Okay. Okay, so yeah, let me just say something application. Okay, so first application is that the Euler phi function, right? So remember the phi of n is defined to be Euler number, which is less or equal to n and the factor and the coprime to n, right? So one can write it as m less or equal to n, and where m and not coprime. Okay, and you just count one. Okay, so by this theorem, right, if you choose this guy to be 1, right, and choose and the k to be n and the n to be m, right, so you get 5n, right? So by plugging, you get 5n equals to this this equation, right? So you're dealing with something by definition, right? Let me just write down. You get a d mn mu of d, which is just summation mu of d. D belongs to n, and which is m less or equal to n, and the d belongs to m. Okay, so this is 1, right? By using this, you get something, and f is 1, right? And then you combine everything, you get d of mu of d, d belongs to n, and the times n divided by d. And then this is a relation between the phi function and the Mobius. You see, oh, you just change this to be 1, right? Summation m, but m is a factor of n, right? So you just change this to be n divided by d. Okay. Okay, so the next is the Ramanujan sum, right? So you see all these number theory functions somehow like they are connected together by some very tiny way, very tricky way that they are actually correlated. So Ramanujan sums. So this is why if you talk about Riemann hypothesis, that the distribution of primes actually spread into different kind of functions. Okay, so let's define CQN, which is the famous Ramanujan sum, a from 1 to q, exponential 2 pi I n a divided by q, where aq is 1. Okay, so you can do the same thing, right? You just eliminate this guy. Okay, so you can check your CQN by using the previous one, right? Previous formula. Then we can prove this, right? So C mu q divided by d, where summation d is basically qn. Okay, so if you choose n to be 1, you get the mu of q. Okay, and so you basically prove something which is really deep. A from 1 to q, and aq is 1. You get exponential 2 pi I a divided by q, which is mu of q. Okay, so this is also a deep relation. Okay. Okay, the deep problems. Okay, so you might think that okay, I should say a deep problem. So you might think that this mu function is trivial, right? So somebody give you a square free, and the square free is not square free 0, even distinct prime factor is 1, distinct is -1. But actually, if you know, actually the problem is that how do you estimate these kind of things, right? How do you estimate these kind of things? Let's say n, where n less or equal to x. Okay, this is very deep, right? Because you need to know the prime factor structure, right? Try to estimate this, right? So this is the very, very deep results. Okay, so this is the unsolved problems. How to estimate these, how to estimate these things. Okay, so this is the famous unsolved problems. Okay. Okay, so the famous Merten's conjecture, I think up to now is still really weird. Is that the mu of n is equal to x? Okay, it's bounded by square root of x for all x greater or equal to 1. And this conjecture is already been disproved, right? But if you plot constant c here, then it's hard to say, right? So I mean, if you choose c, let's say choose 0, 2, and I believe that for all x greater or equal to 0, this conjecture is true, but people cannot prove it or disprove. So I think up to now that people can prove that if you choose as c 0.0 something, then there can be infinite x which violate this inequality, right? But for the constant c, we don't know. Okay, so yeah, this is very deep conjecture that hard to imagine that this kind of function is simple, right? But if you sum of them, like somehow you need to know the prime factor distribution, the prime distribution. Okay, but we can prove something simple. So this is a theorem. Okay, so the theorem says that for all x greater than 0, then I want to bound this guy, right? So previously I want to bound this guy, right? But this is a deep theorem. I cannot bound it, but I can bound this guy. Okay, so famous results. Okay. Okay, so this is weird, right? Because this guy is maybe always plus or minus 1, right? But maybe it's greater or equal to 1, right? Because if you bound it by each guy, then summation 1 over n can be infinity, right? But this guy is actually bounded by 1. Okay, so right, so I mean, you can just choose x to be n for some positive integers, and then let's consider this s of n, right, to be a summation of e of n, and that's equal to n, right? So this is just what? This is just when n equals to 0, right? So let's compute this. Okay. Right, first idea is that it's just 1, right? Because when n equals to this small n equals to 1, then this guy become 1, right? But there's other ways, right? I mean, you can, that by definition, that I can write e of n in terms of the Mobius function, right? So it's d belongs to n, mu of d. Okay, so this equality is really powerful that you always do this. Can give you something interesting. Okay, so that means you can write this guy in terms of n belongs to n, d of n, mu of d. Okay, so once you need to sum different n, which is a factor of d, right? So you can do this. You can do this is d less or equal to n, and the mu of d, right? And now there's a factor that how n divided by d. Okay. Or basically, let's using this. Okay, so this n divided by d means that the greatest integer less or equal to n divided by d. Okay, so let me just write down. So this means that the greatest integer less or equal to t, right? You can check this because now I choose any d which is a factor of this. So mu of d is preserved, right? But how many of them is bounded by this guy, right? Okay. Okay. Right. Okay, so now this function, right? This guy. So this guy is at most different from n divided by d plus 1. Okay. So that means let's see, right? So this is s of n, right? So let's say if you write s of n minus n times mu of d divided by d, right? These guys, if you replace this by n divided by d, then you at most lost 1, right? So this is less or equal to summation d less or equal to n, right? The mu of d and the n divided by d minus this, right? Okay, and then this is at most lost 1, right? So it becomes this. You can change it that's the minus less or equal to minus 1. Okay. So this is less or equal to -1, but basically you just n. Okay, you don't care. Yeah. So yeah, you can check because if d equals n, then these guys are the same, right? So the only difference comes from is d less or equal to -1. Okay, and then you get some one of them. You get everything is bounded by 1, right? So it's this. Okay, so this n of d summation d less or equal to n 1 over d. It's bounded by n minus 1, right? It's bounded by n minus 1, right? Plus 1. Okay, hopefully you guys can see why this is true, right? Because this guy minus this guy is this guy, right? So this is just n minus 1 plus 1 is n. Okay, so divided by n, then you prove that the d less or equal to n, mu of d divided by d is less or equal to 1. Okay, so this is the non-trivial results. Okay, so non-trivial bound for the Euler, for the Mobius function. Okay, so let me just quickly introduce another function, which I think is really important. Okay, so maybe next time.